Okay, the next thing that we want to discuss is the propagation of plane waves in lossy media. So let's go back to the beginning of the chapter where we first introduced the wave equation. This is for a uniform plane wave. It's for a wave that the electric field points in the x direction and it propagates along the z direction. So under those cases, we found that our wave equation reduced to the following, where we have a second derivative with respect to z minus gamma squared e sub x of z is equal to 0. And now in the previous section where we talked about lossless media, we basically said this gamma squared is equal to minus omega squared mu epsilon c, where epsilon c is epsilon prime minus j epsilon double prime, and epsilon double prime is sigma over omega. So these are all relationships that we derived in this and the previous chapters. But remember that in the lossless media, sigma is equal to 0. So that made the gamma to not be complex. Gamma became real because the permittivity was real. So all we're doing different here is we're saying, okay, we're no longer going to say we have a lossless media. Now we have a lossy media, meaning that it's not a perfect dielectric and it does have some non-zero level of conductivity sigma. So because of that, we now say that since gamma is complex, we can express it as a complex number, alpha plus j beta. And alpha will be known as the attenuation constant, and beta will be known as the phase constant. So now if we come up here to equation 7.62, and equation 7.62 is just the relationship that was derived directly from Maxwell's equations to get the wave equation. So we have this relationship between gamma squared and epsilon prime, epsilon double prime. So now we're going to take alpha plus j beta and we're going to substitute into this equation 7.62 for alpha squared. So that's what's going on here. So we've got alpha plus j beta squared. When we solve that, we get this equation. And then that's going to be equal to the right-hand side of equation 7.62. So if you look here, both of these expressions, which are equal to one another, are complex. So they have a real part and an imaginary part. So when working with complex numbers, what you do is to solve equations, you set the real parts equal to one another, and you set the imaginary parts equal to one another. It's almost like if you were solving, say, a vector equation where you have different components. So the complex plane works the same way. You have your real part and you have your imaginary part. So what the next slide shows is this top line is the real part and the second line is the imaginary part. Doing some algebra and solving these two equations simultaneously, you can basically get a solution for alpha and beta. So alpha is equal to this expression here, and beta is equal to this expression. Beta will have units of radians per meter because remember it is the oscillatory part, and alpha will have units of nepers per meter because it's going to be an exponential decay. So you can see that both alpha and beta are functions of mu epsilon prime, epsilon double prime, which is a function of sigma, and then one of them has a -1 and one of them has a +1. And notice that omega enters here prominently. So both alpha and beta are frequency dependent in their magnitudes. So now if we go back to talk about the H field. So the electric field then, this was the solution, equation 7.68. This was the solution that we get when we solve that second order differential equation. It's just going to be an exponential. Now, the difference here in the lossless case is in the lossless case we had e to the minus jkz. Here we have e to the minus gamma z. And then gamma can be broken down into its real part, which gives us minus alpha z, and its imaginary part, which gives us minus j beta z. So if this portion, the e to the minus alpha z, were not here, what we would have would be a traveling wave. When the e to the minus alpha z is added, it has the effect of attenuating. So this is a traveling wave, but it's attenuated. So the magnetic field can then be determined by applying the equation that says that the curl of E is minus j omega mu h, or by using the equation that tells us that h is k cross E divided by eta. Except in this case, the difference is we're going to use eta c, the complex form of eta, because we have not assumed we have lossless media. So for our expression for eta, instead of mu over epsilon, it's mu over epsilon c, where epsilon c is complex. And then the second part of this expression shows the substitution that's been made for epsilon c, which is epsilon prime, and then this term here to the minus 1/2. So the main difference then is that both the wave is attenuated and the impedance eta is also complex. So this is nothing unusual. We've seen complex impedances before in circuits. So this is exactly the same thing. We just have a lossy media. It's not going to act as a perfect dielectric, but it will have some conductivity. So if we then look at the magnitude of E, which means that this traveling wave part will average out, and we're just looking at sort of the magnitude of the phasor E over the amplitude starts at 1 and then it decays, and it decays as e to the minus alpha z. So it is as if the wave entered the material here at z equals 0. And as it propagates into the material, it has an exponential decay. That exponential decay has a decay constant of 1 over alpha, and so that's referred to as sigma or delta S. Delta S is called the skin depth. Basically, delta S is the value of Z at which the electromagnetic field is 1 over E of its original intensity. So skin depth is a common property. Notice that it's a function of alpha. Let's remember what alpha was a function of. It was a function of the conductivity, the dielectric permittivity, mu, and omega. So what this means is that the skin depth, or the depth into which an electromagnetic wave will penetrate a lossy material, is a function of omega. So the distance del S is called the skin depth, and it characterizes how deeply an electromagnetic wave can penetrate into a conducting medium. Now, this is a fairly interesting concept because, for example, if we look at the case of a wire that carries an electric current, if the wire is a poor conductor and the frequency is very high, then what happens is the current that's in the wire is actually only in the outer shell of the wire. Okay, here is a table that summarizes low and high frequency approximations for lossy media. So you can see a summary for any medium, and then what happens is if the medium is lossless, meaning it's a perfect dielectric, we have the following expressions. If the medium is low loss, where epsilon double prime over epsilon prime is much, much less than 1, we have the following expressions. And if the medium is a good conductor, we have the following expressions. So this is for alpha, beta, eta, the phase velocity, and the wavelength.